Imagine everything you've ever known. Every galaxy, star, and planet exists inside a black hole. Not near one, inside one. Sounds like science fiction, right? But some leading physicists propose this jaw-dropping idea could explain the Big Bang, dark energy, and even the shape of our universe. Today, we're diving deep into one of the most mind-bending questions in modern cosmology. Is our universe inside a black hole? Get ready to challenge everything you thought you knew about space and time. Buckle up! This journey through the cosmic rabbit hole is going to change how you see reality itself. Black holes have always fascinated scientists due to their mysterious nature. They are regions of space where gravity is so strong that nothing, not even light, can escape. But here's the twist. According to some theories, black holes don't just trap matter, they might spawn entire new universes. When matter collapses into a singularity, could it bounce and inflate on the other side, like the Big Bang? This is the foundation of the black hole cosmology hypothesis. From our point of view, inside this new universe, we would perceive it as an expanding space, just like we see with our own universe. In fact, the equations governing black holes and those behind the expanding universe share shocking similarities. So, what if the birth of our cosmos wasn't a singular explosion, but rather the formation of a baby universe inside a parent black hole? The Big Bang theory tells us that the universe began from an extremely hot and dense state and has been expanding ever since. But it leaves many unanswered questions. Like, what came before the bang? Some scientists, like physicist Nikodem Poplawski, suggest the Big Bang might actually have been the result of matter collapsing into a black hole in another universe. In this view, the singularity at the heart of a black hole is not an endpoint, but a gateway, a tunnel to a grand new universe. This could help resolve some of the troubling infinities in standard cosmology and provide a natural mechanism for cosmic inflation. It also removes the need for a mysterious cosmic beginning, because our universe is simply the continuation of another one. Most people think of black holes as destructive voids, but general relativity suggests a different story. Inside a black hole, time and space behave in ways we can't fully comprehend. As matter falls past the event horizon, it seems to disappear. But what if it's actually moving into a new realm? Some theories propose that inside each black hole, the laws of physics reorganize, giving birth to new dimensions and new universes. In this view, black holes aren't the end of information, they're cosmic seeds. This would mean our own universe, with its own unique set of physical laws, constants, and particles, could be the inside of one such cosmic bubble, a universe birthed through gravitational collapse. This theory isn't just wild speculation, there are intriguing observational clues. For instance, the shape of the universe appears to be flat, but a black hole interior would look flat to someone inside it, even if it's embedded in a curved space. Also, the mysterious dark energy driving the universe's accelerated expansion could be explained by the repulsive gravity inside a black hole's core. However, testing this idea is extremely difficult. We can't exactly peer out beyond our cosmic horizon to confirm we're inside a black hole. And many mainstream scientists argue the theory lacks empirical support. Still, it offers a compelling alternative to standard cosmology and invites us to rethink what we mean by space, time, and origin. If our universe is inside a black hole, what does that mean for the nature of reality? It could imply that black holes across the multiverse are continually giving rise to new universes, each with slightly different properties. This could be the engine behind the multiverse, making our universe just one of countless others, all sprouting from black hole seeds. It might also offer a solution to the fine-tuning problem, why our universe has the perfect conditions for life. If trillions of universes exist, it's no surprise that one of them looks like ours. Ultimately, this theory reshapes not just our scientific models, but our philosophical understanding of existence. Are we living in a black hole? Maybe. And if so, the real question becomes, what's outside of ours?
Let's take a deeper look at one of the key elements supporting the black hole universe theory, the Einstein-Rosen bridge, or what we commonly call a wormhole. Einstein and physicist Nathan Rosen proposed that black holes could be connected to white holes, hypothetical regions that spit out matter instead of pulling it in.
If a black hole is a tunnel, then its other end might very well open into a new region of space and time, a new universe. In this framework, our universe might have emerged from the white hole end of a wormhole. Though no white holes have ever been observed, the concept gives a theoretical backbone to the idea that black holes could serve as bridges to other realms. The math that underpins this theory is surprisingly elegant. General relativity equations allow for the formation of wormholes and nested universes. The curvature of spacetime within a black hole can, under certain conditions, flip to create an inflating space on the other side. In fact, when modeling a spinning black hole, a Kerr black hole, the equations predict multiple regions, some of which resemble expanding universes. This means the math doesn't just allow for this possibility, it suggests it. Still, these are abstract solutions. Whether they reflect real physics or just mathematical curiosities remains a matter of intense debate among cosmologists. Think about this. Black holes could be not only cosmic death traps, but also cosmic wombs. In this metaphor, black holes are giving birth to new universes, each with slightly tweaked physical laws. This idea is sometimes called cosmological natural selection, a concept proposed by theoretical physicist Lee Smolin. Universes that produce many black holes create many offspring universes. It's a wild blend of Darwinian principles and cosmology, and it suggests that our universe may have properties that maximize black hole production, not a coincidence, but a cosmic reproductive strategy. If true, it's not just poetic, it's revolutionary. To understand what happens at the heart of a black hole or at the beginning of our universe, we need a theory that unites general relativity with quantum mechanics, a theory of quantum gravity. Currently, such a theory doesn't exist in a final form, but approaches like loop quantum gravity and string theory offer clues. Loop quantum gravity, for example, proposes that the singularity at the center of a black hole is replaced by a bounce, a transition from collapse to expansion. This bounce could literally be the Big Bang, with our universe emerging from a quantum-corrected core. In this view, black holes are time-reversed universes waiting to be born. One of the most puzzling problems in physics is the black hole information paradox. What happens to the information that falls into a black hole? Stephen Hawking once said it disappears, violating quantum law. But more recent theories suggest that information is somehow preserved, perhaps even reborn in another universe. This is where white holes return to the conversation. If white holes are the exit point for matter and information that falls into black holes, then perhaps the data isn't destroyed, it's recycled. The implications are staggering. Every universe could be a kind of data echo, formed from the memory of its parent cosmos. The cosmic microwave background, CMB, a faint afterglow from the Big Bang, is one of the strongest pieces of evidence for the standard cosmological model. But could it also be interpreted as evidence for a black hole origin? Some physicists think so. The near uniformity of the CMB might reflect the smoothing that occurs during the transition through a wormhole or bounce. Slight anomalies in the CMB, such as cold spots and non-Gaussian patterns, may even hint at leftover imprints from a prior universe. It's speculative, but it shows how even well-established data might tell a very different story under a new lens. One radical but increasingly popular idea is the holographic principle, which suggests that all the information within our 3D universe is encoded on a 2D surface, much like a hologram. Where did this idea come from? Black hole physics. When physicists calculated the amount of information in a black hole, they found it was proportional to the area of its event horizon, not its volume. This implies that the universe we experience may just be a projection from the boundary of a higher dimensional space. If our universe is inside a black hole, then its event horizon could be encoding everything we know.
If black holes create universes, and those universes in turn generate more black holes, then the result is a cascading tree of universes, a multiverse. Each baby universe might have different physical constants, different particles, even different dimensions. This idea dovetails with string theory, which predicts an almost infinite number of possible vacuum states. Our universe could be just one bubble in this vast cosmic foam. And if this model is accurate, then there's no center of the universe. It's all branching endlessly from collapse to creation. We're not the main event. We're one bud on a blooming cosmic tree. Inside a black hole, time doesn't flow as we know it. General relativity predicts that as one approaches the singularity, time essentially stops from the perspective of an outside observer. But from inside, time might still tick forward, just in a radically different way. This has profound implications for how we view the universe. If we're inside a black hole, then our now could be someone else's eternal frozen moment. It may explain the arrow of time, why entropy increases, and why we can remember the past but not the future. Time, in this model, is born from collapse. The black hole universe theory also intersects with another mind-bending idea, the simulation hypothesis. If our universe emerged from highly ordered conditions within a black hole, then it may resemble a kind of cosmic code or program. The repeating structures across scales, spirals in galaxies and DNA, for example, could be signs of recursive algorithms playing out. While speculative, it leads to provocative questions. Are universes inside black holes designed? Or is the structure a natural consequence of mathematical inevitability? Either way, it suggests a universe shaped by patterns deeper than atoms in energy, a code beneath the cosmos. One reason we don't see evidence of a universe inside a black hole is due to the cosmic censorship hypothesis, which suggests singularities are always hidden behind event horizons. That means we could never directly observe the origin of our universe because it's veiled by a black hole horizon. But this doesn't mean we can't infer its properties indirectly. Like archaeologists uncovering lost civilizations, cosmologists decode the past by analyzing light, structure, and energy. If we find consistent patterns that match predictions from black hole models, it may one day force a radical revision of cosmic history. Could gravitational waves, ripples in space-time, carry signals from parent universes? Some scientists believe so. Just as a bell rings when struck, the birth of a new universe could generate a gravitational echo. These faint signals might be buried in the noise detected by LIGO and other observatories. As our tools become more sensitive, we may detect patterns that don't match known astrophysical sources, clues to a universe born inside a black hole. These echoes would be like cosmic fingerprints left behind by the parent cosmos, offering a new frontier in gravitational astronomy. While black hole cosmology is fascinating, it's one of several competing models. Other alternatives include the ekpyrotic universe, where our cosmos was born from the collision of higher dimensional branes, and cyclic models, where the universe undergoes endless expansions and contractions. Each model aims to address the same questions. What caused the Big Bang? Why does the universe expand? Why are the constants of nature so finely tuned? The black hole theory stands out because it doesn't require a beginning. It simply recycles and transforms, like nature itself. This makes it not just a theory of origin, but a theory of evolution. Here's a mind-blowing twist. If black holes birth universes, and we someday create an artificial black hole in a lab, could we accidentally create a new universe? Theoretically, yes. This raises ethical and philosophical questions. Would that universe have its own time, space, and even conscious beings? Would we be their gods? This is no longer just theoretical speculation. With advancements in particle physics and quantum engineering, creating tiny black holes might one day be possible. The potential consequences, cosmic creationism, are too huge to ignore.
At the end of all this speculation, one poetic truth emerges. If our universe is inside a black hole, then everything we observe, the galaxies, the stars, the cosmic web, is the interior of something else. We are the inside looking out, unable to see the walls that contain us. The very laws we think are universal might be local, tied to the physics of this one black hole universe. It humbles us, reframes our perspective, and expands our imagination. Are we inside a black hole?
The deeper we dig, the more the question itself becomes a gateway to new cosmic truths. Entropy, the measure of disorder in a system, is central to our understanding of time and the universe. In traditional cosmology, entropy increases as the universe expands, creating the arrow of time. But what if entropy behaves differently inside a black hole? Some physicists speculate that the increase in entropy we observe could be a feature of existing within a black hole's interior.
The compression and subsequent expansion could establish initial low entropy, explaining the uniformity of the early universe. As entropy rises, it drives cosmic evolution forward, mimicking time's forward motion. In this sense, time, change, and even memory could be side effects of our universe's unique position inside a greater cosmic object. If black holes can birth new universes, is it possible that every black hole in our universe contains another universe inside? Some theorists suggest that supermassive black holes at the centers of galaxies could be portals to entire new cosmoses. Imagine that! Every swirling galactic core might hide a complete universe within it, each one evolving with its own space, time, and physical laws. This could make our universe a multiversal generator, producing an unimaginable web of realities. If this is true, then looking into the heart of a black hole is like peering into a cosmic womb, an origin point of infinity. To fully understand whether our universe could exist inside a black hole, we have to consider the Planck scale, the scale at which classical physics breaks down and quantum gravity dominates. At this microscopic level, space and time become quantized, and the smooth continuum of general relativity gives way to a frothy, probabilistic reality. A collapsing mass in another universe might reach the Planck density, triggering the bounce that gives rise to our cosmos. This quantum fuzziness replaces singularities with manageable geometries, reinforcing the possibility that black holes don't end in a breakdown of physics, but in new beginnings. The anthropic principle states that the universe must have properties that allow observers like us to exist. Critics often dismiss it as tautological, but within the black hole cosmology framework, it gains new depth. If universes emerge from black holes and pass on slightly altered physical constants, then only those universes capable of producing life, and therefore black holes, would persist across generations. In this light, our universe appears fine-tuned because it is the product of a kind of cosmic evolutionary filter. Only black hole-producing universes reproduce. Life, then, may not be an accident, but a natural consequence of universal inheritance. Inside a black hole, the geometry of space behaves in strange and non-intuitive ways. Some models predict that a collapsing black hole interior could curve into a baby universe with positive curvature, like a hypersphere. To an observer within that space, the universe would appear flat on large scales due to relativistic effects. This could explain why measurements of our universe show near-perfect flatness despite inflation's predictions. The geometry isn't just a mathematical curiosity. It's key to understanding how space is structured and why things appear the way they do from within a black hole's event horizon. If we're inside a black hole, what does that mean for the standard model of particle physics? One hypothesis is that the constants we observe, like the speed of light or the strength of gravity, could be local properties of our black hole universe. They may vary from one black hole universe to another. This could explain some of the unsolved mysteries in physics, such as why the Higgs boson has the mass it does, or why neutrinos have such small masses. These frozen constants might be side effects of how our specific black hole froze and inflated into a new reality. A common question is, if we're inside a black hole, why can't we detect the outside universe? The answer lies in the structure of space-time itself. Once inside a black hole's event horizon, no signal, light, radiation, or gravity can escape back out. This boundary creates an absolute information wall. Inversely, we can't receive signals from beyond the horizon of the universe we live in. It's a one-way street. The parent universe is forever sealed off, and unless we discover some novel way to access or perceive beyond our cosmic boundary, we may never confirm our cosmic origin directly. We are locked inside, at least for now. In early universe physics, symmetry breaking explains how forces like gravity, electromagnetism, and the nuclear forces separated. Within the black hole universe model, this breaking could occur during the transition from collapse to bounce. The birth of a universe might involve a high-energy state where all forces are unified, only separating as the universe expands and cools. These phase transitions could be influenced by the conditions of the parent black hole, making every universe's rules a function of its birth conditions. Our universe's laws, then, may be as much a consequence of its ancestry as of natural law. As computational physics and quantum simulations advance, some scientists are exploring the idea of simulating black holes in quantum computers.